In this section of the workshop, we'll explore the exciting world of time series forecasting. We'll look at 3 different methods for creating forecasts, learn how to evaluate which method is best, and finally, we'll apply these methods to the county-level COVID-19 data that we've been working with. Time series forecasting is all about estimating future values of a time series. The time series forecasting tools we'll explore today all work against the space-time cube. However, unlike our previous analyses, where we were looking for patterns or trends in the existing data, time series forecasting is a method that extends the space-time cube with additional data. So how can we actually estimate values for the next time step? If you recall, each column or location of the space-time cube represents time series. Let's visualize the location's time series with time on the horizontal axis. This is a more common way to represent a time series. Here we have data for January through July, and our goal is to create estimates of the values for August and September, for example. So how do we accomplish this? The tools look at the existing data in the time series, and this is called the training data. We then fit a model to that data, really a mathematical model. Next, we extend or extrapolate that model to the future in order to create the forecast. Now, there are many ways to create a model of the data. We can use several methods to model and then choose the model that fits the data the best. The selected model, the one with the best fit, is used for the forecast. There are 3 tools in ArcGIS Pro that help you perform time series forecasting. Each of these tools uses a different model, or in other words, a different approach to forecast. The 3 tools are Curve Fit Forecast, Exponential Smoothing Forecast, and Forest-Based Forecast. Let's begin with the simplest of these tools, Curve Fit Forecast. It works by applying one of 4 equations or curves to the training data: linear, parabolic, exponential, or Gompertz, which you can think of as an S-shaped curve. A single curve type from one of these 4 can be selected, in which case the method you choose is applied to all locations in the cube. Or you can ask the tool to auto-detect the most appropriate curve type for each location in your cube. Let's see how the curve fit forecasts work with our COVID data. As you can see, I'm in the time series forecasting toolset of the space-time pattern mining tools. I'll use the curve fit forecast tool. I'll browse to that space-time cube that Lauren created for us. Here's our COVID cube. For the analysis variable, we'll stick with daily new confirmed cases per 100K. Only going to forecast one time step into the future. I want to save my forecasted results into a new space-time cube. Remember, we're appending new time steps. I'll call that curve fit. And here I could choose which of the 4 curve types I want to apply, or I can let the tool auto-detect the best curve type at each location. Now I can withhold a few time steps for validation purposes, and we'll talk about that in a few minutes. And let me go ahead and run the tool. Now, since we are applying multiple methods at every location in the entire US, this tool does take a few minutes to run. So in the interest of time, I've already run the tool, and let's start to explore the results. Starting here in the West, the tool produces custom pop-ups where I can see the original values, the fitted values, which are in orange here, and then looking at the future values. You can see the exponential method was applied here. In this case, the linear, a linear curve fit best. Here, parabolic. As we move farther east, exponential fit best. As we're approaching the northeast, we have both a parabolic and Gompertz in some locations. Now, clicking around the map is interesting. but we also can symbolize the map based on the type of curve that was fit, the best curve at each location. So linear fit in a good portion of the US, but we see on the east and the west coasts, it required more complicated models of exponential or parabolic. So we saw that the curve fit tool was able to auto-detect the best model, which of the 4 curve types fit best. Let's explore how it was able to evaluate those models objectively. Recall that the known data, the observed data, in each of the time series is known as the training data, and that the tool fits a model to the data, a line in this example, and then uses that model to create the forecast. Of course, the model doesn't fit the data perfectly. How far off the model is, either under-predicting or over-predicting, is called the residual. There's a residual at each time step. So to get an overall idea of how well the model fits, I can square those residuals, add them together, and then take the square root of that sum. This final number is a metric called RMSE, and it really is just a number that tells us how well the model fits the data. In the example here, the line doesn't match the data very well. But if we were to apply an S-shaped curve to this data, I think that the fit is much better. In this case, the RMSE would be lower. Now, we can calculate validation in one of 2 ways. We can calculate it on all of the observed data that we use to train and predict with. This is called the forecast model. And the overall measure of fit, how good the model is called the forecast RMSE in this case. Or we can withhold some of the data from the training set. Basically, not let the model know about some of the data at all. When we forecast, now we have some known values, some observed values that we can compare the forecasted values to. The overall measure of fit in this case is called the validation RMSE. So you choose which option you want in the tool dialog, depending on the purpose of your analysis. The forecast RMSE measures how well the model fits the data. I use this type of RMSE when I'm using the tools in an exploratory sense, when I'm really just trying to describe the structure of the time series. The validation RMSE measures how well the model can forecast. Use this if your goal is to forecast as accurately as possible. Let's move to the next forecasting method, exponential smoothing. This method is very popular in time series analysis. Exponential smoothing works by decomposing a time series. But what does that mean? What does decomposing mean? Decomposing means breaking the time series into different components. It takes characteristics about the time series, such as the level. The level can be described as a set of baseline values that you might expect from the data that you have. It also has something called the trend, which is described as the general difference between the beginning of your time series and the end of your time series, and a seasonality or cyclical component that you might have in your time series. Now, all 3 of these components are used to build a model, and that model is used to build the forecast. The difference between the model and the observations, the residuals, are used to build a confidence interval about our estimate or predicted value. Even though we provide a very specific number for the predicted value, we know there's some uncertainty associated with that prediction. So the confidence intervals give us a possible range of what the true value could be. So let's look at how exponential smoothing works in a little more detail. So as the model is built, an assumption is made that each time step influences the next time step. So the last time step was influenced by the one before it, and so on throughout the history of the time series. Another way to think about this is that every time step is influenced by every time step before it in an exponentially decreasing manner. This exponentially decreasing influence is actually how the level and the trend are determined. If you have seasonality in your data, in this instance, it looks like a 4-step season, that will also influence the forecasted value. If you know the length of the season in your time series, you can specify it in the tool. For example, if you've got quarterly sales patterns in your sales data, then you might specify a season length of 3 months. So let's review how exponential smoothing actually generates a forecast. The value at a particular time step is influenced by the most recent time step, but it is also influenced exponentially by all of the time steps before it. If there's seasonality in your data, the forecasted value is adjusted for the influence of that seasonal effect. So in this case, the seasonal value 4 steps back actually pushes the value of our forecasted value down. And if we keep incrementally going back to the previous seasons, they will also influence the forecasted value. And finally, we have a forecasted value. This process is repeated to generate all of the forecasted values. Now, exponential smoothing is a tried and true method and has been around for many years. Many people also know it as the Holt-Winters method. Just as before, exponential smoothing is calculated for each location independently. So that was a quick explanation of exponential smoothing, and probably the most important takeaway from this method is that it's highly suitable for seasonal data. Let's see how exponential smoothing does with our COVID-19 data. So here I have the exponential smoothing forecast tool. We'll browse to our COVID cube. For the analysis variable, we'll choose daily new confirmed cases. Again, I'll only forecast 1 step into the future. I'll save my forecasted results into a new space-time cube. I don't know the season length, so I'll let the tool choose it for me. I'm going to exclude 2 time steps, and we'll go ahead and run this tool. It's applying this exponential smoothing forecast method to all 3,000 plus counties in the US. It's writing the output features now. And let's explore some of these results. Again, starting in the West Coast, we can see that this method is providing pop-ups of the original values, the fitted model, the forecasted values, and that confidence interval that we talked about. Moving to the Great Plains, and moving farther east, we can see, at least in my judgment, that this exponential smoothing forecast model seems to be fitting the data better than those simple curve fit methods did. The third tool is called forest-based forecast, and it can be very effective for more complex time series that may not be well described by simple curves or by seasonal patterns. Now, as the name implies, it uses the random forest machine learning algorithm to produce a time series forecast. Now, we're not going to go into deep details of random forests, but the principles are very similar. So if you've understood the previous tools, you'll get this one also. It uses training data to build a model, but in this case, the training data is used by a random forest model to produce a single forecast point. This tool is guided by a really important parameter called the sliding time window. The sliding time window tells the tool how many time steps to use as your training set. What happens next is that the sliding time window starts moving forward, time step by time step, producing forecasted values as the window moves forward. You may notice eventually the tool starts producing a true forecast, a forecast for observations that we didn't have data for initially. And if we bring those forecasted values down, that becomes the model itself. So here we see both the model patterns and the forecast. Like before, the model is run individually, location by location, across the cube. Let's use the forest-based method with the COVID-19 data. So I'll choose the forest-based forecast tool. Browse to our COVID cube. Choose the analysis variable. We'll forecast one time step into the future. We'll save our results into a new space-time cube. I don't know the time step window in these data, so I'll let the tool help me pick a value for it. I'll exclude 2 time steps for validation and go ahead and run the tool. Now, something interesting about this tool is you'll see that it runs fairly quickly, even though it's a more complex model. It's writing those output results, which we'll explore next. And let's begin on the West Coast again. The pop-ups tell us all of the parameters of the forest-based model. And again, these fits look quite good to me. We can see that the model that we're fitting to the data is matching the original data quite closely. And just like the exponential smoothing method, the forest-based approach also gives us a confidence interval. So to summarize, there are 3 time series forecasting tools. Curve Fit, which is the simplest to run and interpret. Exponential Smoothing, which is well suited for capturing seasonal or cyclical patterns. And forest-based forecast, which really has no underlying assumptions about your data and can capture more complicated patterns and trends. However, it is a little more difficult to explain and interpret. So these tools are admittedly a lot to digest. How do we know which tool to use and when? What if some of our locations in the study area have simple linear trends while other locations are more complex? Fortunately, there's a very straightforward workflow for solving this problem. You can run all 3 forecasting methods and then use the Evaluate Forecasts by Location tool. It'll pick the best model for each location in your space-time cube. The workflow is really straightforward. You run Curve Fit Forecast, save the results in a new cube. You run Exponential Smoothing Forecast, save the results, run the forest-based forecast, and save the results. Next, you decide if you're interested in explaining the time series or if you really want the best forecast. And then the Evaluate Forecast by Location tool looks at all 3 of these input cubes on a location by location basis and picks the best forecast at each location. Let's do this with the cubes we've already created. I'll use the Evaluate Forecast by Location tool. I'll input the Curve Fit, Exponential Smoothing, and forest-based forecast cubes that we created. I'm going to save the best forecast at each location into a new cube. I'm interested in this in the exploratory mode, so I won't use the validation RMSE in this case. And I'll go ahead and run the tool. It's looking at each of those cubes that we created, picking the best model at each location. And now it's writing our output feature class and output cube. Let's explore these results. So again, starting on the west coast, we can see that the forest-based model fit well here. It seems to match the data quite nicely. Moving into Texas, the forest-based forecast method again. Moving into the Midwest, it seems like the forest-based method has been chosen quite often here. So there was one where the exponential smoothing method fit. The Gompertz fit best in this location. So while we can click around the map, we also can symbolize this layer on the best model. Here I'll look for the forecast method. And we can see that the forest-based method was chosen as the best model in the vast majority of the country. The exponential model was chosen on occasion, and also the Gompertz. So let's review what we've learned today. We explored 3 methods of forecasting. We discovered how to evaluate those different forecast methods, and then we applied all of those methods to our COVID-19 data. I hope you find these methods useful.